Hi all, welcome back to Systemverilog sessions. In this video, I'm going to discuss about coverages in Systemverilog. So now onwards, we'll be discussing on coverage topic. So if you have any doubts in coverage or if you get any doubts while watching my video, you can just ask me in the comments. Okay, let's start with the coverage first. So when you hear the word coverage, what you will understand? Just think of a coverage as how much of a certain area you have covered. Okay. Coverage means how much of a certain area you have covered or tested or explored. So I will give you one simple example to understand the coverage. For example, you have a car. Okay, this is car. Okay, you have a car and you want to test this car, that how well it will works on different types of road. For example, you have a highway, you have a city street, and you have some dirty roads. Okay, you want to test this car, that how well it will drive on different types of road. Now what this coverage will do? Coverage ensures that you have driven on all types of road. Okay, coverage ensures that your car has driven on highway, and your car has passed this city street, and your car has passed this dirty roads. So basically coverage is used to measure the performance of the test, right? So that you are confident in the car's performance in all the situations. So what coverage is doing here? Coverage tells us that what we have tested and what we have not tested. Okay, coverage tells us what we have tested and most importantly what we have not tested. So it's about how much area we have covered based on the test. Okay, it's about how much area has been covered by the test. See here, coverage will tell you that whether your car has passed highway or not, whether your car has passed this city street or not, whether your car has passed this dirty roads or not. It will tell you what you have tested and what you have not tested. Similarly in Systemverilog. So here your car is your design. Okay, in Systemverilog your car is a design, your Verilog or HDL code, and this highway and your whatever the roads, these are all the test. You want to test your design, right, in all the possible ways. So here I said area, how much of a certain area you have covered by the test, I said, right? So that area is nothing but your functional or code. Okay, the functionality of the design or your code of the design. So how much of the functional or code has been covered by your test bench, by your test. Okay, so this is a simple example to understand the coverage. We will discuss in detail. So we'll see the definition now. What is coverage? Coverage is a simulation metric used to measure the progress and completeness of the verification process. So what is the purpose of coverage now? Purpose of the coverage is to ensure that the design behaves as expected under the various conditions and scenarios. So by tracking the coverage, we can identify the areas that may have been overlooked or not tested thoroughly. So it will ensure that the design is well verified, so that it will minimize the chances of bugs. Okay, it will minimize the chances of undetected bugs. And it plays a crucial role in providing a clear understanding of how well the design has been verified, and helps in identifying the areas that have not been sufficiently tested. Okay, and here we have two types: code coverage and functional coverage. Code coverage and functional coverage, these are all the two types of coverages. So what is code coverage? Code coverage is a basic coverage type which is collected automatically. It tells you how well your HDL code has been exercised by your test bench. So what is code coverage? Code coverage is a basic coverage type which is collected automatically. It tells you how well your HDL code has been exercised by your test bench. That means the idea is to track whether all the lines, branches, conditions and paths in your design's source code have been triggered by your test or not. Okay, the purpose of the code coverage is to check all the lines, branches, conditions and expressions or paths in your design has been covered or not, has been triggered by your test or not. This will be checked by using the code coverage, and this is collected automatically by the simulation tools. We are not going to write any code for the code coverage. Okay, it will be collected by the simulation tools during the simulation. So this is about the code coverage, and here in code coverage also we have some types we will discuss. Okay, after covering the code coverage and functional coverage, we will go to the types. So next, functional coverage. Functional coverage measures how well the functionality of the design has been covered by your test bench. So this functional coverage is used to ensure that the design's intended functionality have been verified through various scenarios or not. So various scenarios in the sense edge cases or any boundary conditions or any typical use cases. Okay, so this functional coverage is more focused on measuring whether the key functional behavior of the design have been tested by the test bench or not. Okay, the functional behavior of the design it will check. So what is this functional behavior? Functional behavior in the sense the design features. Okay, so for example, when you have a design and you want to verify that design, how you will verify? First we will write the test plan or verification plan. So in what is there in the test plan? There will be all the test of the design, right? And those tests depends on what? Based on the design features. For example, you have a memory. You have a memory means memory. What memory will do? We will write into the memory. We will read from the memory, right? Those are nothing but the test only. So those are nothing but the features of the memory. So in the test, what you will write? One write test and read test and write followed by read test. You will write the test for different test scenario, right? So those tests depends on the features of the design. So first we will collect the features. First we will extract the features from the design, then we will write the test based on the features, right? So functional coverage is typically defined based on the requirements or features, based on the requirements or features of the design that need to be verified. Okay, this is about the functional coverage, and here also we have types. So now we will discuss the types of coverage. So here you can see the types of code coverage. So statement or line coverage, block coverage, branch or decision coverage, conditional or expression coverage, toggle coverage, FSM coverage, and path coverage. So these are all the types of code coverage. And in functional coverage, we have data oriented and control oriented functional coverages. Okay, so these are all the two types of functional coverage, and these are all the types of code coverage. We will discuss each type in detail in the next slide. So now we will see the types of code coverage. The first one is statement or line coverage. So what is this statement or line coverage? Statement coverage includes procedural statements, continuous assignment statements, conditional statement, and branches for conditional statements. So statements in the design. For example, here I have a code snippet. Always at passage clock, begin if and else statement. So this is called one if statement or line, and this is one statement. Again, this is one statement, this is one statement. So all these statements or lines has been covered by your test bench or not. So this is the design code. Okay, by giving some stimulus to DUT, whether you have covered this line or not, this will be collected by statement or line coverage. Okay, this will be measured by statement or line coverage. And next one is block coverage. What is block? A group of statements. A group of statements which are in the begin, end, or if else, or case, or wait, or while loop, or for loop, etc. So these are called block. So block coverage checks all the code inside this block has been executed at least once during the simulation or not. Okay, so that is nothing but block coverage. Here I have example. This is if block and this is else block. So whether this block has been covered or not. Here it will not check for whether this condition is true or false. Okay, it doesn't matter whether the condition inside the block evaluates to true or false, as long as the block itself is executed. Okay, so it will not check for the true or false condition. It will just check whether this block has been executed or not, if block has been executed or not, or whether else block has been executed or not. So this is block coverage. So the third one is branch or decision coverage. In branch coverage or decision coverage, conditions like if else, case, and the ternary operator statements are evaluated in both true and false cases. So this is important. Okay, statements are evaluated in both true and false cases. That means what? Branch coverage ensures that both the true branch and false branch are executed. Means both outcomes of the condition are tested. As the name suggests, branch, right? Branch means one true branch will be there and one false branch will be there. So both outcomes of the condition are tested or not. That will be covered by branch or decision coverage. For example, here I have a if block and else block. So this if A greater than B. If this condition is true, then only this branch will be executed. Or if A is less than or equals to B, that is false branch. So if this is executed, then only this block will be executed, right? So this is about the branch or decision coverage. And then conditional or expression coverage. As the name suggests, it will search for the conditions in the code. Okay, so this coverage focuses on evaluating the individual conditions within an expression. Okay, it measures whether the each condition in the larger expression has been evaluated in both its possible states. States in the sense your true or false state. Okay, so conditional coverage is the ratio of number of cases evaluated to the total number of cases present. And For example, if an expression has Boolean operations like XOR and OR as follows, the entries which is given to that expression to the total possibilities are indicated by expression coverage. For example, here I have a out expression out is equals to X XOR Y or X and Z. Here actually I have three conditions, right? XOR operation I have, and AND operation, again OR operation. What this conditional or expression coverage will do, it will check for each condition in the expression. Okay, it will search for individual conditions in the larger expression. Here X or Y, that means this is two variable, 2 to the power 2, four conditions we have, 1 1 1 0 0 1 or 0 0. So four states we have, and here also two variables, again 2 to the power 4, and again OR we have. So these are all two variables now. So total uh, 4 into 3, 12 cases we have. So what conditional coverage? Conditional coverage is the ratio of number of cases evaluated to the total number of cases present. For example, 12 cases is present, but you are giving only some 4 or 5 cases. So this is the ratio of number of cases evaluated to the total number of cases present. We are not going to calculate any calculation here, but this is done by the tool. Okay, this is about the conditional or expression coverage. And the fifth one is toggle coverage. Toggle coverage gives a report that how many times signals and ports are toggled during a simulation run. Toggle coverage gives a report that how many times signals and ports are toggled during a simulation run. That means this coverage helps us to verify the activity of various signals in the design. So it will tell whether the signals have undergone any changes or it remained constant during the simulation. And it measures how often each signal or port changes its value from 0 to 1 or 1 to 0. 0 to 1 or 1 to 0 is nothing but toggling, right? So it will measure how often each signal is changing. Okay, and if the signal toggles frequently, it indicates the active usage of signal. That means this signal has been actively used in the design. And as I said, it also measures the activity in the design, such as unused signals or signals that remain constant or less value changes. Okay, so this is about the toggle coverage. And the next one is FSM coverage. FSM means finite state machine. So FSM coverage reports whether the simulation run could reach all of the states and cover all possible transitions in a given state machine. So it will help us to verify whether we have reached all the states in the design or whether we have covered all possible transitions in the given state machine. So state means this indicates whether all the states of the FSM have been visited by the DUT or not. If some state is not being visited, then either test bench needs new stimulus or there is some redundant state in the design is not being used. Okay, so whether we have covered all the states in the design or not, if any of the state is not reached, then we have to provide the stimulus from the test bench, or there is some redundant state in the design which is not being used. Okay, and transition means this covers all possible transitions from one state to another. Transition is nothing but the paths to reach from one state to another. So in FSM we know that there can be various paths through which a state can move to another state. For example, in APB only we have three states: idle, setup and access, right? So to reach from idle to access, there is a two way. You can directly reach from idle to access, or you can go from idle, setup and access. So I'm just giving the example. Covering states only won't tell us whether all paths have been verified or not. That's why we need transitions also. So we have to cover transitions also. Okay, this will be covered by FSM coverage. And we will move to the functional coverage now. So we know that functional coverage deals with covering the functionality or features of the design. So it's a user defined metric that tells about how much of a design functionality or specification has been covered. So here we have two types: data oriented functional coverage and control oriented functional coverage. So we will discuss one by one. The first one is data oriented functional coverage, a method of data collection where sets of variable values at a particular point during simulation are recorded. So as the name suggests, data oriented, we will record the data during the test, whether this data has covered or not, whether this data has hit or not. So it will cover the datas and it will record the datas during the simulation. And a test plan should be written in advance to capture the functionality to be tested based on the design specification. Then particular data value and data value transition scenarios reflecting that functionality are constructed. So we have discussed this. We need the test plan first, because in test plan we will include all the tests. Based on the test only the coverage will be decided, right? So we have to write the test plan in advance to capture the functionality to be tested. So based on that we can cover the data, whether this data or particular pattern of data has been covered or not, we can check. and it is purely a test bench construct. Test bench construct means here we can get the data oriented coverage by writing the cover groups, coverage points, and also by cross coverage. So this cover groups, coverage points, these are all the constructs. So it's purely a test bench construct. By writing this we can get the functional coverage, data oriented functional coverage. And the example is writing a different data patterns in a register. So we know that in register multiple bit fields will be there. So each bit field will do one operation, right? So when we configure some bit field, that will perform some operation. So in order to complete the register, in order to fill the register, we have to give some data. That is nothing but a pattern. So whether that pattern has been covered or not, whether we have provided that data or not, we can check that by using the data oriented function coverage. It will collect the data. So if we provide that data, it will tell that this data has been occurred, this data has been covered. Okay, so this is nothing but a data oriented functional coverage. And control oriented functional coverage means a method of data collection where specific temporal behaviors that occur are recorded. So here this is a control oriented functional coverage. Here we will check the temporal behavior of the design. What is this temporal behavior? Temporal behavior in the sense when time is involved or when clock cycles or time period is involved, that is nothing but a temporal behavior. So here we will check whether the sequences of behaviors have occurred. Sequences means what? A list of expressions that spread over one or more clock cycles. So when the sequence is spread over one or more clock cycle, that is called as a temporal behavior, right? So after some event you want to collect that data. After triggering some event you want to collect that data. That is nothing but your control oriented functional coverage. Okay, so here event means what? Some sequences of expression. After this sequence happened, you have to collect that data. So that you can get by control oriented functional coverage. So here we know that sequences how we have to write the sequences by using assertions, right? So control oriented coverage can be specified using the assertions, and therefore it is sometimes referred to as assertion coverage. And since assertions can include flexible sequence specifications, it is useful to keep track of how often a particular sequence was satisfied by each possible temporal behavior. So we know that control oriented functional coverage will check whether the sequences of behaviors have occurred. So to write the sequences, what we need assertions. So that's why it is useful to keep track of how often a particular sequence was satisfied by each possible temporal behavior. For that we need assertions. Okay, so that's why this control oriented functional coverage is called as a assertion coverage. And the example is reading a register to retrieve reset values after releasing a system reset. So here how time is related after releasing a system reset. So this after releasing a system reset is nothing but the temporal behavior, right? So we are waiting for the reset signal deassertion. So when the reset signal is deasserted, we are going to read the data from the register. So that means we want the default values. So after releasing the reset, we are going to collect the data of register. So this is the example for control oriented functional coverage. So here in the control oriented functional coverage, time will be involved, and in the data oriented functional coverage, time will not be involved. Okay, so this is related to the data and this is related to the time. And control oriented functional coverage can be written by assertions, and data oriented functional coverage can be written by writing the test bench construct. That is nothing but cover groups or coverage points. So we will see how to write the data oriented functional coverage. Okay, and this can be done in assertions. So we will discuss more in detail in next video.